Okay, I will summarize what I did last time. I introduced what is digital system. I talked about 3 types of signals: analog, discrete time and digital. You are not able to hear. Adhyaman is not able to hear, sir. Anybody is not able to hear?
No, sir. Not be able to hear.
Nobody is able to hear. My God.
No, sir, we can hear you. We
You
can hear
cannot
you.
hear me. I don't have any control. I am a simple person coming with the lecture material. So it's all Mr. Kannan, who is our technical person. Sir, you only argument கேட்கலையா?
இல்ல இல்ல இனிமே கேட்கும்.
Yeah, are you able to hear me now, Adhyaman?
Yes, sir. We can hear you.
See, when you make a complaint, you have to also tell me when this complaint is sorted out. You say I am not hearing, and then he does something to improve the matter. Then you say, sir, it is now coming, you should say. Otherwise, how will I know? Okay, now you are able to hear me, all of you? Yes? Yes. Anybody not hearing me?
Yes.
Mathura, College, are you able to hear me? Mathura? Ah, very good. Okay. What we did was I defined 3 types of signals: analog, discrete time and digital. And we said digital systems are very popular because it's easy to build. I do not want to go with the impression that digital systems are more accurate than analog systems. Precision or accuracy of digital systems not necessarily better than analog systems. All I said was it is easy to improve the precision and accuracy of digital system by adding some more stages, identical stages.
சொல்லுங்க.
They are all similar. So if I want to improve from 8 bits to 10 bits, I need 2 more stages of what I had already. Whereas analog is a lot of efforts. So the output improvement is not proportional to the effort you put. Effort is more for a little improvement. Otherwise, there is no question of don't go about telling professor said digital systems are more accurate than analog systems. That is a wrong concept, not wrong idea. Number 1. Number 2, now noise performance is also better in digital system because we have levels separated by a large amount of voltage. So if the voltage falls within a range of high or within a range of low, it will be easily read as low voltage or high voltage. Whereas analog voltage is continuously changing amplitude. So when there is a change in the amplitude, you don't know what was the original amplitude. So noise performance is better in digital systems. Again, it is always possible to make good noise-free circuits in analog also, but all I am saying is the efforts required are more compared to digital systems. That is all I want to summarize. Then I said parameters by which you define digital systems are size as compact as possible, cost, everybody wants to buy everything cheap, power dissipation, you want power dissipation to be very low, and speed, high speed performance. All of these are also possible in analog systems, but cost cannot be compared here. Analog systems are generally more expensive. That is why most people design digital systems. 90 to 95% of all circuits today are digital, but the extra 5% is a very critical component, and that is why if you go to any industry for a job, if you are an analog designer, you get much more salary than a digital system designer. So don't neglect analog. Just because you are listening to me, don't go about telling everybody digital systems are better than analog systems. That is why I have not learned analog systems. That is a wrong perception. I want to clear it right away. Because you go to your teacher who teaches analog and tell the professor said digital is better, he will slap you. Okay? Be sure about that. Okay. We already told about course content. The books I told you, I will repeat again, and two major books. There are lots of books are available, but two major references will be Morris Mano, Digital Design, and C.H. Rath, Fundamentals of Logic Design. These are very simple books to follow, always taken for the first course. There are other books like TOCCI, TOCCI, Wakerly, so many other books. You go to library and look for digital books, you will find at least 50 books. Whichever book your professor recommended, whichever book you feel comfortable with, you can use it. Not much different. Okay. Today what are we going to do? We talked also about the block diagram of a digital system. Main processor works on digital numbers. Digital means numbers. Any digital signal, once you have converted from analog through A to D process, it becomes a set of numbers. And the numbers are manipulated easily in a computer. So it is a number manipulation. A filter is number manipulation. Convolution is a number manipulation. Everything is a number manipulation. So you do that number manipulation, then they become digital signals with output, converted back to analog signal by using digital to analog converter. There are many levels of digital design. It is not a simple design. For example, you want to design a system like computer. How many levels are there? We call it a system. Computer is a system. I cannot design a computer at one go. It's not that you design something, put together and it will work. No. First of all, you have to break it into subsystems. For example, CPU, memory, input and output devices. These are called subsystems. Then you go to subsystem. Can you design a one-go subsystem? No. It will break it down further. A CPU can be, for example, you take one of these examples. A CPU consists of control logic, arithmetic logic unit, etc. These are called components of a subsystem. These are called subsystem functional block. These are functional blocks or modules. And again we break it down. Arithmetic logic unit can be arithmetic unit, logic unit, etc. These are called modules of the functional block. Modules. And then you go to further, see what is an arithmetic unit? It consists of adder, subtractor, multiplier, shifters, etc. These are functional blocks. These are again a subsystem of functional block. These are called actually subsystems, functional blocks, basic units. These are called basic units. The names do not matter. You can call it anything. And a basic unit can be defined using our logic. And your basic unit is defined using gates, flip-flops, counters, etc. They found the basic unit. Again, they form, you cannot just say adder I want. I should define a circuit for an adder. How does it connect intercomponent? How do you connect the gates to make a circuit so that it will work as an adder or a logic unit or a multiplier? So that will be circuits. So next level is circuit level. Interconnection of gates, etc. If it's a sequence, if it's a combinational circuit, you only connect these gates, multiplexers, memory, etc. If it's a sequence circuit, you connect, you go for a sequential machine, what is called this digital sequence circuit is defined by a state diagram. From state diagram you go to the design. And then finally, how do you get this? Using transistors and everything else. Devices and transistors, devices, generally devices can be transistors, devices. Basically devices make gates, devices make flip-flops, devices make counters, etc. So devices and components. So, is it that unit system design is easy? It's not that simple. You have to break a system into subsystems. You have to break a subsystems into individual modules. You have to break the module with basic units consisting of adder, subtractor, etc. And then that you can form by gates, etc. Of course, circuits and gate, this is all the same. We don't have to define separately. 5 and 6 may be same. And then these are made using devices like transistors, MOS devices, etc. This is how you do. It's called hierarchical design. Step by step. Today we have one more level hierarchy. It's called functional description using hardware description language, HDLs. You have VHDL, Verilog, etc. which you use in order to describe these systems and then translate them into hardware. I'm not even talking about it now. We'll talk about it later on. That is the functional description of hardware systems using hierarchical, hardware description language, HDLs. There are two types of HDLs, Verilog and VHDL. Okay, this is how we do, and The other thing I told yesterday was, this one I didn't say, books I told but I thought I will write it down. The other thing I said was precision. I have two levels, basically digital is 0 and 1. Zero need not be 0 volts. It is either 0 volts or off of a switch off or whatever. Let us say flag down in a non-electronic system. You put a flag saying something is inside for you. For example, if you get a mail, you get a message. There's a message, unread message, SMS. Or if you go to the email, new mails are given by block letters, bold letters. So you know this is an email. So it's always a way of telling you there is something new. Off. One is on of a switch, 5 volts or whatever voltage you choose, on of a switch or flag up. And so many other possibilities are there. I am not listing all of them. But then, this is only 2 levels in a digital system. That means I have a signal which can take 0 volts or 5 volts. 0 volts is 0, 5 volts is 1. Now I cannot represent everything I want to represent. For example, I want to design an arithmetic unit. I have lots of numbers. I cannot have all the numbers 0 and 1. So I need to make more point combinations. So what I do is, I combine this into different positions. For example, we said 0 and 1 are not good enough. So we have this is called bit. So binary digit. Binary digit is called a bit. One bit I can only represent 2 levels. Nobody wants this. Do you want an adder to add 1 and 0? No. Supposing I have more numbers, more precision is required, I can increase it to 0, 0, second level. This is first bit or most significant bit, MSB. MSB stands for most significant bit. And then 0, 0, 0, 1, 1, 0, 1, 1. Now with this I can represent 4. If it is only 0 and 5 volts, this is 0 volts, this is 5 volts. Now this is 0 volts, 1.25 volts, 2.5 volts, 3.75 volts. This precision is not good enough for me. Add one more bit. 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0, I'm sorry, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. This is 7. So the same 0 volts to 5 volts, 0 volts, 1.25 divided by 2 is 0.625, then 1.25. You can add 0.625 to this, whatever, 1.875. You can do the calculation. Finally, it is 0.625 less than 5 volts. 4 point, if you subtract 0.625 from 5, it will be 4.375. So these 8 levels. And then you go on increasing. So this is the least significant bit. What you have at the end, on the right hand side. What you have at the left hand side is more MSB. So this is MSB. This is LSB. That is why today we are having 8-bit adders, 16-bit adders. We have computers work on 32 bits, 64 bits, 128 bits. All modern computers have 128 bits, and even more. Otherwise, you can't do this. Precision is required. If you are doing a computation involving aerospace, simulation, You need lots of numbers and lots of equations. You need to have it. So I need as many bits as possible. Of course, when you have a lot more bits, you need more memory. We will see this later. Speed gets affected and so on. But what is the point of having a 2-bit adder? 2-bit adder I don't need. Even 1-bit adder I don't need. 2-bit adder also I don't need. 0, 0, 1, 1, 1, 0, I know how to do that. 3 bits also I don't need. So 8 bits okay, a little bit. That is why microprocessors are 8 bits, 8085. 8086 is 16 bits. And all other higher level are more than that. This is how it works. Okay? Now, this is the summary of what I did yesterday, but this one I did not do yesterday. This one I told you, but I wrote it today, and I wanted to emphasize this precision so that somehow I got the impression that I said digital systems are better than analog systems. No, it is not true. You can have an easier design of higher precision by adding 1 bit. If you divide these 5 volts, 8 levels or 4 levels, or you use an extra bit, identical stage, 1 more flip-flop. Whereas analog, the effort required is much more to improve the performance. Same thing is noise. Because digital systems have noise margins which are very high, there are only 2 levels, 0 volts and 5 volts. I can allow up to 0.8 volts as low level. So anything within that range is read as 0 level, and 5 volts, anything up to about 3 volts is read as high. Whereas analog, we don't know what is stored. So when you read it, you don't know if it's accurate or changed. Generally, we charge a capacitor. How much it is leaked, we don't know. That's all. Now let us move on today. Numbers. I said digital computers work with binary numbers. Anything in digital computers or any digital system is binary numbers. You write programs in C language, whatever language, Java, doesn't matter. What the computer needs is binary. You have to convert it using compilers and assemblers. For your convenience, you can write in English language. Even your word that you are typing, the word processor is English, but the computer doesn't understand. The computer stores it in a file, it's converted into binary using a code called ASCII code. You know that. So we have to convert everything into binary. So computers work with binary. So we have to know a little bit of binary arithmetic. All of us know this. 0 and 1 are 2 bits of a binary. So, but we are used to decimal numbers in normal life. In everyday life, we are using digital numbers, decimal numbers. So, how do you convert a decimal number to binary number? All of you know this, but quickly I will go through this. I will take an example that way. Suppose I have a number, let us say what? 41 binary. How do you know this? 41 decimal, I mean. You always put a base, it's called a base. 10 is a base for decimal number. 2 is the base for binary numbers. 8 is the base for octal numbers. 16 is the base for hexadecimal numbers. You can have any base also. You can have a 5, base of 5, 7, 9. It's up to you. You like 5, base of 5? You do your arithmetic using base of 5. Nobody can question you for that. Provided the results are finally decimal numbers. Okay? So 41 decimal, when you convert to binary, I can only have 0 and 1 in a binary. So what do? I divide 41 by 2. This is 20 by remainder 1. 20 cannot be handled with binary, so I divide it by 2, 10, remainder 0. Again divide 2, so the result till the quotient becomes 1, remainder 1 or 0, and remainder becomes 1 or 0. 5, 0, 2, 1, 1, 0. So now this is MSB because 41. So the number is 100101. That is the conversion of 41 decimal into binary number. How do you know it is right? This is position. In decimal number, 41 means 4 to the power of 10 to the 1 plus 1 to the power 1 into 10 power 0. So decimal base, 10 is the base. So 10 to the 1 is 10, so it is 40. 1 into 10 power 0 is always 1. Anything to the power 0 is 1. So this is 1, so it is 41. Here we will do 2. So this is 2 power 0, which is 1. 2 power 0, 0 into 2 power 1, 1 into 2 power 2, 0 into 2 power 3, 0 into 2 power 4, 1 into 2 power 5. 2 power 5 is 32. 2 power 4 is 0, I don't have to take into account. 2 power 3 is also 0, I don't take into account. 2 power 2 is 1, so it is 4 times 1, 4. Wait a minute. This is 1, yeah. This is 2 power 0, 2 power 1 is 0, I don't take into account, this is 1. This is, oh, what happened? Let me see. In a hurry, I would have missed something. This is 1 is 1 into 2 power 0, 0 into 2 power 1, 1 into 2 power 2, 0 into 2 power 3, 0 into 2 power 4, 1 into 2 power 5. This is 1, this is 0, this is 4, this is 0, this is 0, this is 32. But, yeah, this is different. This is 41, 20, 10. I think I missed something. What is that I missed? 2 power 5 is 32, right? 32 plus 4, 36 becomes 37, whereas I should get 41. This is 2 power 0 into 1. 2 power 1 into 0, 2 power 2 into 1, 2 power 3 into 0, 2 power 4 into 0, 2 power 5 into 1, this is 32 plus 4 plus 2, 4 should be here, 4, 0, 2 power 1 into 0, 2 power 2 into 1, which is 4, okay, 32 plus 4, 36, 37. That means this is wrong. I use this 1, 0, 0, 1, 0, 1, 1, 0, 0, 1, 0, 1. This is 20, 1, 10, 0, 5, 0, 2, 1. So it is 1, 0, 0, 1, 0, 1. Oh, this is correct. Let me see these notes. There is a mistake here apparently. I did not use 41. I used 26 into 26. Yeah, 1, 0, 0, 1, 0, 1. 41. Now, that is 2 power 0. 2 power 0 is 1. 2 power 1 is 2. 2 power 2 is 4. 2 power 3 is 0. 2 power 4 is 0. 1, 0, 0, 1, 0, 1. 1, 0, 0. From this side it is 1, 0, 0, 1, 0, 1. This is 3, 4, 5. Somebody has a solution for this? I think I made a mistake here. 2 power 2 is 4. 1 plus 4, 5 plus 4 is missing somewhere. Yes, sir. Tell me. Huh? You have to be unmuted. Say it. So muted, unmuted, muted.
We counted from I think bottom to top.
Huh?
Sir,
It should be from bottom to top. It should be
bottom
read
to
from.
top.
Any doubts? You can raise your hand.
Oh, this is
It should be read from.
yeah, 1 0
Sir, it should be 101001.
Yes, that's right.
It should be 101001.
1 0 0
From bottom to right.
1 0 0 1.
Bottom to top.
001.
Okay. This is 2 power 0, 2 power 1, 2 power 2. Muted, muted. Yeah. Yes. 1 plus 8 plus 5, 32. Yeah. Thank you very much. I should have written this way. Now this is LSB, MSB. What is remaining MSB? Thank you. You and you, whoever. This girl and that. You are from Indore, right? Indore. And this, you are from which college you said, but you are muted you said. How is that you are able to hear? Yeah. Okay, thank you very much for both. So I did the LSB, MSB, ulta. Yeah, I know. Sometimes it happens to professors.
That was one participant by name Archini, sir.
Huh?
Archini and Ayush were interacting with you.
Yeah, thank you, Ayush and what is the other
And
name?
Archini, yes.
Archini.
Yes, sir.
Thank you both. You'll get half a point extra in your final exam. No, just kidding. No, we don't give marks free. Thank you very much. Okay, it slips. There is a proverb in Tamil, even for elephant, it can slip and fall. I'm not an elephant. I'm just saying. It's equivalent proverb in Tamil. Okay. Okay. I have done it maybe this teaching for this course I have done probably 20 times in my entire career. If it has to happen, it has to happen. You can't do anything about it. Okay, now let us do fractions. I hope I will not make a mistake. Anyway, I have my Ayush and Achin. Where is my, yeah. Fractions, how do you do? Let us do the fraction of 0.6875 says. 0.6875 is a fraction I want to convert into binary. How do you do that? See, binary can have 1 0 1 0 like that. So I have to get a 1 or a 0. So what do you do? I first multiply by 2. This becomes 1.195. I don't know.
Very difficult to move my head. Okay, I'll take that. Okay.
And
Anything else?
you multiply this by 2, 6875, 1.350. How will come? Yeah. 0. What is this? 286825. 6875. It says 1.350. 1.350. This again would start like this here. Multiply by 2. 1.375, correct. 1.375. So this 1 will be retained. I take 0.375 next time. Multiply by 2 becomes 0.750. Multiply this 750 into 2 becomes 1.5, right? 750 and you take 1 off, you put 500 into 2, it becomes 1. So this is again 1011. This is highest. In this case, this is this way. In this case, this is this way. Wrong. Who is saying wrong? That is right, I say. 685. You can also do this way. You remove 0.5 from it. 0.5 is 10 power minus 2 power minus 1. So 1 gone and it is 1875.
Sir,
Yes. Yeah, tell me.
your content control is only visiting. You are not visible to us.
I'm not listening to what?
Because there is a machine there. Now it's
You are going to tell me
now
something?
now it's okay.
That's what I said. If somebody else is saying no, that indoor guy, you want to say something? I'm not hearing you. Unmute.
யாராவது உட்காரணும் எனக்கு நிறைய இருக்குதா. See, I'm facing some problem. சரி வா.
See, you can do it this way, man. 2 power minus 1
Raj.
plus 2 power minus 2, 2 power minus 3, 2 power minus 4. This is 0.5, this is 0.25, this is 0.375, this is 0.0625, like that it goes. Now how much does it have? 6. So you have 6875, you subtract 5, you get 1875.
நெட்வொர்க் ரொம்ப மோசமா.
No 0.25 here, so you put the second digit 0, then you take that off, then you have how much? If you take that off, 0.25 if you take that off, it's not there, then 6875 minus 0.5 is 1875. 1875 has 1875 has 0.375? No. What is this? I'll do it again. Confuse me. I'll do this. So first let me convert it into binary to decimal. So I will have a fraction which is 1011. 0.1011. If you want to convert it to fraction, what do? You multiply by 2 into 2. Okay, this is 1101 2202. No, something is wrong here. 6815 I want to do. So 1011 will become, this is not done here. 6005 is done as 0.1 into 2 power minus 1 plus 0 into 2 power minus 2 plus 1 into 2 power minus 3 plus 1 into 2 power minus 4. So this is 0.5. This is 0.25, this is 0.25, half of 0.25 is 1.25. 1 into 0.125, half of that is 1 into 0.0625. So this you know you have to add them all. 0.5 plus 1 to 0.25 plus 0.600625. Add them, because 5, 7, 8, 6. 6875. That's what we started with. 0.6875. Is that right? It is conversion of 1011 into decimal number fractionally. Now reverse. I took 6875, then I multiply by 2 becomes 1.350. So I keep this 1 on that. 0.6875 converted into binary fraction. You multiply by 2 first. So this becomes 1 point. There is something wrong here. But 1.375. Is that right? 1.375 plus 1. So this 1 will be 3. So you take this 1 as the MSB here. This is that digit. What do you make? This digit. Then now I will remove this and multiply 3.75 into 2 becomes 0.750, which is, so there is no 1 here, so this is the second bit. So now I take this 0 off, multiply by 2, 1.50. So I take this 1. So this 1.50, I take this 1 already, so I put 500 times 2, it is 1.000. That is how it is. So repeated multiplication by 2, here repeated division by 2. You get the integer numbers, repeated division by 2, fraction is repeated multiplication by 2. So this is what I get. 1011. What did I do here? 1.3750. 750. Correct. And 1.5, I did it all. So it's 1011. Same thing here, 1011. So the number is 1011. So this the fractional part is 1011, integer part is 101001. So it is 41.386875 will mean 101.1011. The reverse conversion is easy by giving the weights 2 power 0, 2 power 1, 2 power 2, here 2 power minus 1, 2 power minus 2, 2 power minus 2. It is not a very major exercise, but it is better to know that. Okay, once you have the decimal number, you know any number of base, now you have the formula. The two other bases normally used are 8 and 16. 8 is called octal, the other one is called hexadecimal. Octal is 3 bits at a time because 8 is 2 power 3. So you want to express this octal number 101 001 1011. You want to express an octal, you group them into 3 bits. Bit is only used for binary digit. Octal and all we call digit. So this is, first digit is 1, second is 5, 101 is 5. So 51 octal. And this one is 101 5 100 is 4. By 4 octal. So now I have, what is the original digital number? 41.6825. Decimal is this to the base 10.
इसमें रिकॉर्ड करना होगा.
What? Somebody saying something? Yes? Somebody is saying something? Hello? Who told me something? Or you are talking to yourself? Colonel, somebody was talking. Who said something? You did? Indore? Indore, did you talk? You, sir? Nobody talked. Then why did you hear some noise? I heard, so I thought you talked. Okay, this is decimal. This is equal to 101,001,1011. Binary. It's equal to 51.54 octal. Hexadecimal is grouped into 4. Hexadecimal, 0 to 9, after that we have A, B, C, D, E, F. So this is 1001 is 9. 0010 is 2. This is 1011. 1011 is 1001. 101. 10 is 10. This is 11. 11 is A is 10. B is 11. C is 12. D is 13, E is 14, F is 15. So 1011 is 11, B. Okay? Is okay? Any questions? Now another, how will you convert one of these numbers, small exercise for 2 minutes? Who will come up with this number converted into base of 5? Quickly, take 2 minutes. Convert this. Convert this into base of 5.
Okay.
How do you
Sir,
do
one
that?
moment, sir. Someone is disturbing the class. I'll just disconnect him.
Oh. So I just wanted to ask them a question. Did you get the question? No, first work done, let them work it out. And after 2 minutes I will ask the answer. Convert that number into number to base of 5. Base of 5.
So which number?
This number, convert 41.6875 decimal into a number with base 5. One minute.
ரமேஷ் யாருக்காவது ஃபோன் பண்ணி கொஞ்சம் அங்கே என்ன ஆச்சுன்னு பாரு.
Can you do this?
Hello, is all able to hear Professor, please?
Yeah, they are. Somebody's already started working there, I can see.
No, sir. There are some few people who are actually disturbing the class coming in between.
Yeah, but then I gave the problem. They must be hearing me. 2 minutes later we can unmute them, so I want to get the answers.
Yes, sir. I have unmuted everyone, sir.
It's not going to take a lot of time.
Hello. Can everyone hear hear Professor, please? Please answer.
Yeah.
Yeah.
Yes, sir.
Yeah, please do
Yes,
this.
what the going?
Who
Yes,
has
sir.
the
What the
answer?
going on and off?
If somebody has an answer, raise your hand. Somebody has an answer? Hey, somebody has an answer? Yeah, tell me what is the answer. Tell me.
131.3204.
What is that?
31.3204.
Say it
Base
again, I
5.
didn't hear you properly. What is that?
131.
Yeah, the base of
131.
This
Base
number?
of 5.
Yeah. What is the answer?
Yes, sir. I'll
131.
repeat, sir. 131.3204.
Let us cross check this.
Vaibhav, do you want to say something, Vaibhav?
I got one answer. Let me check that. How do you do that? 1 into 5 power 0 plus 3 into 5 power 1 plus 1 into 5 power 2. That is 0, 1 plus 15, 5 power 2 is 25, 41. Very good. Fraction 0.3204, 3 into 5 power minus 1 plus 2 into 5 power minus 2 plus 0 into 5 power minus 3 plus 4 into 5 power minus 4. 5 power minus 1 is what? 1 over 5. 1 over 5 is 0.2. Is 0.6. 0.6. 5 power minus 2 is 1 over 25. 1 over 25 is 0.4, 0.04. 1 over 25 is 0.204. 0.4 into 2, 0.8. This is 0. 5 power minus 4 is how much? 25. 5 power 4 is 5 into 5, 25 into 25. Oh, this is 25 into 25 is too much. 125, 50. 625 I think. 625.
Yes, sir.
1 over 625 is how much? 1 over 625. Somebody has a calculator? 1 over 625. 4 over 625. 4 over 625. Somebody give me the answer for this.
That's it.
Huh? What is 1 over 5 is 625?
0.0075.
Huh? 0.0075.
0075.
Okay, I
Yes.
assume that is right. 75, right? 0075
Yes.
will be say?
Yes. Yes. Yes.
Okay, 0075 into 4, right?
Uh, fully 0.075.
Uh,
Whole calculation 4 by 625 equal to 0.0075.
0.0075.
0075. 75.
Okay, add them. 75, 8, 6 and 75. Correct. Very good. You know how to do it. That is great. Fantastic. So we can have any number. Let us have the base of 7. Later on you can do at home. If you convert the base of 7. See, the problem is you should remember this will not have anything. How much is this? This is now 131.3204 you said. Hey, 3204 you said, correct. So none of these digits will be more than 4. 0, 1, 2, 3, 4. That is what means by base of 5. Base of 10 is 0 to 9. Base of 16 is 0 to 15. Base of 11 is 0 to 10. Base of 3 is 0 to 2. That is all you should remember. You should never get an answer with a base of x or n where any digit is less than n or n more than n. It should always be n minus 1 maximum. That is the mantra here. That is all. But generally we don't use all these. It's only a mental exercise. For computer we use binary to octal and binary. Nobody is also using octal these days. Binary hexadecimal. You should know how to convert decimal into binary, binary to decimal, and how to convert binary to hexadecimal, hexadecimal to binary. And again today there are circuits for this. You don't have to know anything these days. You don't have to know. Why are you spending time? Because there is an input converter, code converter in any system. So computer, you don't think about these things. You type any number you want in decimal and it tells the right values. Similarly, you type ASCII code. We'll talk about codes next time. You type ASCII code, it will convert into, you type English or Hindi or German or Tamil, it will convert into ASCII code. That's all. That is why they say this processing, that processing. Nowadays Google has, you want to write something in English, translate it into Hindi, it's possible. Called transliteration. Transliteration. Okay. I think we have fairly established a base. Next thing we need to do is, I don't want to go on doing all these bases. Already we have done enough. And all of you look smart, so you know all these things. Have you all read all these things earlier? Yes or no? Have you read these things earlier?
Yes.
Yeah. Anybody has not read this? I think it is in high school physics nowadays. Or computer science. In high school they have computer science. I don't know why they have computer science in high school. You don't need them. You should teach both and more of mathematics and physics and chemistry. Rather than that, they teach computer science, which is a waste of time. My opinion. Okay, anyways, nobody takes my opinion. They decide. Okay, next thing is how to represent a number. Number representation in computers. Because when you write numbers, they can be integers or fractions, or integer and fraction. Integer and fraction together is called a real number. All of you know that. Real number. As if others are not real, unreal. Everything is. Integers are real numbers. Real numbers mean you can also have fractions. Okay. Next is When you represent a number in a computer, it need not be only positive. So far we have been talking about positive numbers. We didn't even say positive. We simply took numbers and assumed they were positive and doing it. But in computers we need to do the sign bit, because when we do the calculator, we have to subtract something from something, add something, or you want to add a negative number. So we need to know sign of a number. So how do you represent sign of a number? Sign the numbers. One is called sign magnitude representation. You give the number 1 bit for sign. So generally last bit MSB is sign bit. So it is 0 for positive numbers, 1 for negative numbers. So if you have a number, let us say 4 bits, 4 binary digits. When I say bit, it is a binary digit. So it is 0, 1, 1, value is 3. If you put 0, no, not point. This is sign bit. These are magnitude bits. So this is positive 3 plus 3. When you put 1 followed by 0, 0, 0, 1, 1, 1 is sign bit which is negative, this is 3, so this is minus 3. It's called sign magnitude representation. In sign magnitude representation, you represent positive numbers and negative numbers. So if the number of bits is there, you have to reduce 1. For example, you have 8 bits, I can represent from 0 to 255 normally, but if I take the sign bit, I have only 7 bits left, so it is 0 to 127. Positive 0 to 127 or negative 0 to 127. That is not a very convenient way of doing it. So we have 2 other systems. One is called ones complement, all of you must know this, ones complement numbers. So again I will take the 4 bits, put 0, 1, 1, 0, 0, 1, 1. I know that this is positive and this is 3. How do I represent the sign complement of this? We invert each bit. It is ones complement is 1, 1, 0, 0. Invert each bit becomes ones complement. Appears this negative number is wrong. Well, I will talk about negative numbers in one's complement. I only says one complement means you invert the bit, every bit. There's a 2's complement. So which is 1's complement plus 1. So in this case 0, 0, 1, 1 is the original number, 1's complement is 1, 1, 0, 0, 2's complement is, add 1 to this, 1, 1, 0, 1. I can also get this right away from here. You copy the first, all the bits up until the first one you encounter. and then you invert each bit. For example, I will give you another number, 7-bit number, 11000010. One's complement, I didn't say anything about positive or negative so far. This is 001101. 2's complement, I have to add 1, which becomes but the trick is to take this number, which is the original number, copy the first bit, copy all bits until you encounter the first one, which is this, and then invert every bit. 11100. So you can either find the 1's complement and add 1, or you can look at the number, copy all the digits except up to the first one you encounter, including that you copy, then from then on you invert every bit. That is called 2's complement. What is the advantage of doing this? Now you will see the 2's complement number, the 1's complement number, if you do including sign bit, it is very easy to do subtraction. You know subtraction in decimal numbers. Binary numbers also you can do subtraction. It's not a big deal. The problem is you need an adder and a subtractor. But when you have one logic, one circuit, which can be both adder and subtractor, subtraction and addition, it is easy because hardware is reduced. So we can convert the numbers, all numbers that you feed into a computer are converted into 2's complement, and then all the arithmetic is done using 2's complement, and the result comes out. Before the results comes out, it is converted back to the original number. So 2's complement is the most common way of doing arithmetic in a computer or a calculator or a microprocessor. So we will do 2's complement. Now we have to talk of positive numbers and negative numbers. Here also we have 0 bit, 0 is a positive number, 1 is a negative. So for example, if you take see, what you do is, you are given a number of numbers. For example, you take decimal numbers. It is called 2's complement, it is 9's complement. It is 10's complement. So I have a decimal system first. Decimal system, I have, let us say, 99 minus 72. So it is 727 is the answer. But I convert it into 10's complement because the decimal number base is 10. So I should convert it into 10's complement. 2's complement because it is a binary number. So it is 10's complement is the highest number possible with this, so it is 100. I am talking about negative numbers. So 72 will be represented as 100 minus 72, which is 28. Which is right? 100 minus 27 is 72. Now 27 is or 1's complement will be 99 minus 72 is 27. This is 9's complement. This is 10's complement. Now you want to do subtraction. You add this number. Original number is 99. Add 28 to that. What is the original answer? 27. Add, not subtract. You have 127. But I can only handle 2 bits, 2 digits. This is a 2-digit number, this is a 2-digit number, so my answer should be only 2 digits. So I discard this carry. So subtraction in complement system is addition. First I have to convert it into the complement number in that system, then add it. So there is 1's complement I have to do. 87, what is that? 99 minus 72. 72, 1's complement is how much? I said 27. Add again I discard this 1, but because 1's complement is 1 less than 2's complement, I add an extra 1. This 1, here we discard this 1, this 1 we bring it back and make it 27. So the answer is same. Whether it be 9's complement or 10's complement, this is 10's complement, this is 9's complement. Both ways the result is same. In the first case you convert the number into 2's complement, mean the negative number which is to be subtracted. Number to be subtracted you convert into 2's complement, add them and discard the carry. In 9's complement case, you again convert into 9's complement the negative number which is to be subtracted, add it to the original number, you get one carry, that carry cannot be discarded, this has to be brought back and added. So the answer is same in both cases. This carry is called end around carry, EAC. End around carry. Okay, we will do binary 2's complement and 1's complement in the next lecture. Also codes. What are codes and how do you use them? What is the advantage? The advantage of 2's complement or 1's complement or 9's complement and 10's complement or 7th complements and 8th complement. Any system where base of 8, I can have 7's complement, 8's complement. Base of 5, I can have 5's complement, 4 complement. Any base you can have a complement system. I will tell you what it means physically also tomorrow, next lecture, what it physically means and how is that addition, subtraction turns into addition. That also I will show you in the next lecture. After that we will talk about binary numbers and then the codes. And then after that I am going to have one class full of problems and discussions. Okay, now any questions? I think this today's lecture, second part, mainly after the hierarchical design, I went into the binary and conversion and all that. That part is very familiar to all of you or most of you. So it must be easy for you to understand this. I am very happy that somebody answered the question rightly. Also I am very happy that you pointed out the mistake in my addition process, a conversion process. That is very good because you are alert, you are not sleeping. At 5 o'clock, 5:30 in the evening, if you don't sleep, that's a big compliment to me. Okay? Anyway, I want you to ask me some questions and make some comments. Well, that way I know the class is active, class is live, not dead. Anybody, just say something. Yes. Tell me, sir. Sir, you have to unmute them. Kanan. Kanan is trying to talk. Unmute problem is a lot of noise comes through.
Sir,
Yes.
sir, functional description, that is hardware description language, is used to represent the hardware.
One more time.
Represent
Say.
hardware description language is used to represent the hardware in program way.
Yes.
There is two types is there, you said. What are
Yes.
the two types I seen here?
VHDL and Verilog. Yes.
VHDL and
V.
HDL, Verilog.
Verilog. We are. These are the two types. Today, big circuits like microprocessor or your cell phone chip, you can't do this hierarchical design, subsystem design, circuits. It's going to take forever. So you describe the whole process, again not in one go. You have to go subsystem by subsystem and you have to put them together, integrate it and all that. But for that you use Verilog and VHDL, one of them. Generally people use Verilog in industry and VHDL in education institutions, that's what they say, but it's not true anymore. Usually now people have Verilog become very common. So you have to know how to describe your circuit in VHDL, what is your requirement, specifications, and then there are tools, very expensive tools, and you have to use them, compile them, and then you have to run a simulation, and then you can put it on a FPGA. If everything works, you send it to foundry to make it as an IC. We'll talk about this some other day.
Okay, sir. Thank you.
Okay. Anybody else? If you don't have anything to say, at least tell what you had for lunch. Yeah. Yeah.
Sir, can you listen me?
Yeah, I can. I can listen to you. Sir, I can listen to you. Before you
Sir,
talk to
another
me, give me from which institution and what is your name, both.
This is Dinesh, sir.
Huh?
This is Dinesh.
Gray.
Another question is,
Huh.
0 volt, 0 is represented as 0 volt, 1 is represented as 5 volt.
Yeah, other way.
This is
Other way, 5 volts is equal to 1 and 0 volts is equal to 0. Okay. Not necessarily.
Positive logic, negative logic. Okay, I understand that there is some band gap is needed. So then noise ratio is not high much. Bandwidth is high, then noise ratio is not too much. That is right.
I won't get your question. Can you make it clearly or send me an email?
Band gap, that is the 0 volt and 5 volt. Subtract it, then 5 volt is gap between them. So what when a noise is added, 0 to if I am using 1 volt is 1.5 volt, then noise 1.5 volt is adding, then the problem is arises. So bandwidth is needed to be high or not.
No bandwidth here. No, it doesn't come. Even in DC it is okay. What I mean is, you have allowance. When you say 5 volts, anywhere above 4 volts you are going to say 1. If you have
Okay.
0 volts, anywhere below 1 volt or 0.8 volts you are going to say 0. So you have an allowance of making errors either because you made it or because it picked up noise or because there is a drop in the voltage as you transmit. These are all the things. First of all, the 0 and 5 volts are examples. Today, 3.3 volts, 1.2 volts, they want to go lower and lower voltages. So 0 and 5 volts are just some examples. You won't stick to them too much.
So we can use one is 1.2 volt also.
1.2 and 0. That is also fine, but in that case the noise margin is less. In that case I can only allow.
There is some bandwidth. What I mean is bandwidth means 0 to 1.25 is the bandwidth. 1.25
It's not a bandwidth, sir. It's not a bandwidth. Bandwidth has something to do with frequency. Why do you confuse? Bandwidth has nothing to do with this. It's a level.
level, step.
How much? Yeah, step size. Exactly, you got the word. How much can
Okay,
it
okay.
change within that level? That's all.
Okay,
Don't use the
the
magnitude. I
step
did
size.
not use the magnitude even once in 2 lectures. Don't use that word with me unless I come to that separately.
Okay, okay. Sir, what I mean is, I again say that 0 to 5 volt, step 64 bit, 2 power 64 possible, then 2 power 64 possible, then I divide the step, then step size is small, very, very small. Then the
Very
noise
small.
is high, very, very small, then noise is high, then it will become very issue. Is
Right.
correct or not?
Correct, but then you have to see the application. See, if that is the
Then,
level at which you are going to pick up your pickup amplifier, your noise level, low noise level, all that is required, then you are capable of that use it. Otherwise, it is very difficult. Yes, you are right.
uh, yes, correct, sir. Then we will increase the 0 to 5 volt to 0 to 20 volt. Then we can divide. That's correct.
But we don't
We can
increase
use.
voltage just for that reason. Because the digital circuits are designed to work with 5 volts maximum.
Oh, low power consumption.
You can't have 100 volts. No.
Yes, sir. Yes, sir. Sir, another one is we are using the subtraction and addition is the same circuit using the two's complement.
Yes.
So when we given the number, then it convert to two's complement, then do work.
Yes.
Or representing is the two's complement itself.
First of all, when the number is failed, the computer converts it into its complement. And
Oh,
that's all the
converter.
arithmetic and give you the result, it converts it back to decimal number, regular number, and then puts you the result. We'll talk about two's
Oh,
complement tomorrow. One's complement, two's
okay,
complement,
sir.
addition, subtraction. Okay.
Okay.
Have a good
Okay,
weekend.
sir. Okay.
Have a good weekend.
Thank you.
Thank you.
Sir, can you listen me?
Yes, sir. Who is this?
To improve the sir, to improve the accuracy, we have to increase the bandwidth, na?
Sir, why are you using the word bandwidth? Where did I
Sir,
use the word
sir, my doubt
bandwidth
is,
in these 2 lectures?
sir,
Yes, sir.
to improve,
Indoor.
to,
Indoor, tell me.
yes, sir. To improve the accuracy, we have to increase the bits, na?
Bits, number of bits. Yes.
Yes, sir. Sir, if we are increasing the bits, then bandwidth also increasing, na, sir? The cost of the system is also increases.
Cost is increasing, but bandwidth. Why will it I can do all this in DC? Sir, this indoor, you want to say something? Yeah, say it. Indoor, please unmute. Indoor. Indoor mic, please. Yes, sir. Indoor mic, please unmute. You want to say something?
Sir, I have unmuted everyone. I have
Yeah.
unmuted everyone.
Indoor, talk now. It's not coming, sir. Indoor wants to say something very badly.
Hello, can you hear me? Can you hear me now? Can you hear me now?
Yeah, tell me, sir, what is that?
Consider a binary number 1101.
1101.
Would you read that as 13 or minus something like that? Minus 5 or 13?
That you should know in advance. You should know in advance what system you are using. It's a pure representation or a sign magnetic representation or one's complement. Unless you know that, the person who designs circuit should tell you it's a two's complement circuit. You
So
can't guess.
it must be predefined in the question.
Huh?
It must be predefined in the question, otherwise we can't assume.
Exactly, sir. You got it right. You hit
Okay,
the nail
thank
on
you.
his head. Right.
Okay,
Didn't
thanks.
hit it
That
on
was
my
it.
head. You hit it on the nail on the head. Right.
Yeah. Thanks.
I will talk about this
Thank
next
you.
time again. Okay.
Okay, fine.
Thank you very much.
Loved your class.
Oh, thank you, sir. It's a good compliment coming from a student. Right.
Okay.
Sir, when will the test next class?
Huh? Next class is
When
next
will the next
Monday.
class?
Next Monday, 4 o'clock.